Today we're going to try 3D printing a machine part out of carbon fiber reinforced nylon. Is it really a viable replacement for aluminum in the shop? Let's find out. Welcome back to Cloud 42. I'm James. If you've followed the channel for a while, and in particular if you've followed my lathe electronic lead screw project, then you know I still have the servo motor hanging out of the front of my lathe on the temporary bracket that was just there for prototyping. I think it's high time we got that thing in the back where it belongs, and to do that we need to make a motor mount. Now I normally would just grab a piece of aluminum bar, design something up in CAD, take it over to the CNC mill and hog it out, but today I'd like to try something a little bit different that's a little bit less labor intensive. This is a 3D printing filament called NylonX. This came from Matter Hackers, and I believe NylonX is their brand name. This is their version of a carbon fiber filled nylon 3D printing filament. The nylon in this is PA-12, and it's filled with 20% by weight chopped carbon fiber. And the carbon fiber does a few things. It adds strength, it adds stiffness or rigidity to the parts. Nylon tends to be fairly flexible, and the carbon fiber makes the parts more rigid. It helps with impact resistance, but it also helps with thermal shrinkage. So as we all know, when you're 3D printing things like ABS, the parts actually shrink as they're printed and as the plastic cools, and that tends to pull them off the bed, which is why it's so hard to deal with bed adhesion with ABS. Nylon has the same problem, but in theory, the carbon fiber fill helps to reduce that shrinkage and helps to make it easier to print. Still, bed adhesion with this stuff is a challenge, and from everything that I've read, the best bed surface to use with this is either glass with the right kind of glue stick or Garolite. And so I actually bought a sheet of Garolite, put it on my printer bed, and we will try that. In theory, you want a bed temperature up around 70 to 80 degrees Celsius, but I've read of people online having success even with a completely unheated bed, though that's not generally recommended. The material prints at a relatively high temperature. This stuff 250 to 260 degrees Celsius, which if you've printed fast with ABS is not unusual, but other brands of carbon fiber, nylon, and nylons in general can print at even higher temperatures, up to 270, 280, or even higher. And so you definitely need an all-metal hot end to print this stuff. The other thing to know going into it is that this stuff is very, very abrasive. The carbon fiber filaments in it will just chew up a brass nozzle. So you definitely need a hardened steel or stainless nozzle on your printer. I picked up a couple of hardened tool steel nozzles, and we will see how that works. This is commonly referred to as black aluminum because it is useful, in theory, for making parts that you would normally make out of aluminum. The tensile strength isn't as high as aluminum, the rigidity isn't as high as aluminum, but for a lot of applications, from what I'm reading, it should be good enough. So let's go design up a 3D printed motor bracket and see if we can get this stuff to print. This is Fusion 360, but the stuff I'm going to show here will apply to pretty much any CAD package. I've already modeled up a motor mount, and you can see I've got a register here and a hole for the motor shaft and 4 threaded holes for the screws, and these are sized for the NEMA 23 size motor package. And then on the other end, I've got a couple of 1/4-inch slots here for mounting screws that'll give us some adjustability. And let me just show how I modeled this. I'm not going to go through all the steps. I basically just started with a sketch with the plan. So the overall size is 2.3 inches square for the motor mount, and then I added 2 more inches. So this is 4.3 by 2.3 inches. And I just sketched out the hole I wanted, the size of the register, the size of the slots, and I put in points for the screw locations. And so then I just extruded that up 1/4 of an inch and then used the fillet to round the corners. Then came back and used this sketch, turned it back on, and used these points with the hole tool to actually create holes the right size for 1032 screws, and these are tapping size for 1032. I went ahead and extruded, using the same sketch, a pocket here for the motor register, and then came back with the Create Thread tool, selected all those holes, and put in threads. And these threads are 1032 UNF, and I marked them as modeled so that it actually put the 3D model of the hole into the part, and you can see that that's there. Ideally, with a perfect 3D printer with infinite resolution, this will result in a threaded hole that you can actually put a screw in. And in some materials you can make that work. My understanding is that NylonX tends to shrink inside holes a little bit, so I'll probably end up running a tap through those. Then the last feature here are chamfers on all of the edges, top and bottom. I did leave them out of the motor register because I want that sharp, but especially every corner surface, except the threads, that touches the bed, I want a chamfer on that. It does a couple of things. It kind of prevents the swelling or elephant's foot that can sometimes happen with the bottom layers. And the other thing it does is give you a place to pry or to wedge a spatula or a knife underneath the print if it gets really stuck to the bed. So I think that's it. It's a real simple design. Let's send this to Simplify 3D and print it. Now, Simplify 3D has recognized that I modeled it in inches and wants to know if I want to convert it and scale it for millimeters. And yes, I do, because in this case, I did model the part using inches because I started with the NEMA 23 motor size, which is specified in inches, specifically 2.3 inches, hence NEMA 23. But the 3D printer works with millimeters, so it has to convert it. So let me hit Control L, and this allows me in Simplify 3D to select any polygon in the part and orient that down to the bed. Click Center and Arrange, and we should be about ready to print. Let's go look at the process settings. Now, this is the first time I've ever printed anything with NylonX, so I'm just working with parameters that I found on the Matter Hackers website and other kind of forum posts with people who have worked with it. So I'm printing it in the left extruder. I've got a 0.4 millimeter nozzle. And for retraction, this stuff does ooze quite a bit. I went ahead and set it to 2 millimeters. We'll see how that works. Layer height, I'm going to print 0.25 millimeters. I have always printed everything at 0.2 millimeters, and I finally realized that I can print at 0.25 or 0.28 or 0.3, and the prints go a lot faster, and most of the time I don't need that resolution. So I've kind of settled on 0.25 millimeter as my standard layer height. And first layer height usually has to be adjusted for different materials. For ABS, I set this a little lower to get a good squish into the bed. For PETG, it's a little bit higher. I'm not really sure what I need for the nylon, so we'll start out at 100% and we can try adjusting that later. This is simple, so I don't need a skirt and brim or raft or anything like that. For infill, we're going to run about 40%. That's probably a little high, but it'll make the part a little stronger. It's probably not going to have a huge difference on the cost for a part this size. Don't need any support. For temperatures, I'm going to run the bed at 60 degrees Celsius. I've seen recommendations anywhere from 0 to or room temperature all the way up to 80. Let's start around 60, see how well it sticks, and adjust from there. And I'm going to run the extruder at 260. That's kind of near the high end of the range. But on my printer, I found, especially with ABS, I have to run way up at the high end of the range to get good layer adhesion. So I don't know if that says anything about the temperature control on my hot ends, but we'll start at the high end and see what happens. Cooling doesn't matter. I actually have the fan unplugged. Now, the G-code has this set of global G-code offsets, and I think most slicers have this. And you can use the Z-axis here to sort of raise the print off the bed if the adhesion is too great, or lower it if you need the print closer. I generally don't use this. I generally use the first layer height. The difference is that this will raise the whole print up without adding any other plastic, where raising the first layer height above 100% will add extra plastic to fill that space. It also will keep track of the resulting height of the part. So if you just raise the z-axis here, your part will probably end up being a little bit taller because it doesn't take into account the fact it's just printing it above the bed. It doesn't know that it's printing it thicker. For speeds, I'm going to run 3,000 millimeters a minute, which is about 50 millimeters per second. In theory, you should be able to run this stuff anywhere from 15, they say, to 60. Other people say 100. I print most things at 100, but we'll start at half that for now. And I think that's all. I think this is a good set of settings. Let's give them a try. We'll take a look here and make sure that everything looks sane. Lay down first 3 closed layers, then we start filling in with the support. We've capped off the register there, and it's going to go up and cap off the top of the part. I think it's interesting to look at how the threads end up being rendered. If you watch as we go up through the layers, it's basically printing an oblong hole that it's moving around to kind of approximate the threads. So for something as fine as 1032, it's not going to be perfect, but it's a starting point. So let's send this to the printer and see what we get. I have my 3D printer outfitted with a Garolite bed. Garolite's a composite material. It's a woven either fiberglass or linen. I'm not sure. I've seen it referred to as both, but it's similar to PC board material. It's an epoxy impregnated fiber board, and this, from what I've read, is really the ideal material to print NylonX and other nylon and other high temperature filaments on. You can also print on bare glass with a PVA glue stick. I haven't tried that. This is the only surface I've tried. I went ahead and just got what was recommended. The other thing that I've done to this printer for success here is I have replaced the nozzles. I took out the brass nozzles and put in hardened steel nozzles because the filament with the carbon fiber in it is so abrasive, it'll just destroy brass nozzles in short order. So I've got hardened tool steel nozzles in there that should prevent that. And I've done a little bit of experimenting to try to figure out how to get the best bed adhesion. And you can see here on the bed, I've got a little mark of shame already where I've pulled some of the surface off with a print. I was doing some test prints on here and got something adhered a little bit too hard because I had the bed a little too hot, and I had the layer height set so the filament was really getting embedded into the surface. I've since raised the nozzles, raised the Z height about 1/10 of a millimeter, and lowered the bed temperature to 40 degrees Celsius, printing the filament, I believe, at 260, and that gave me a pretty decent adhesion to the bed that held the part and didn't allow it to warp during the print, but still allowed me to get it off. So we'll try those settings here. This is a bigger part and we'll see how it goes. Start by wiping down the bed here with 99% isopropyl alcohol. And this is just to make sure there's no skin oil on it from me touching it, or dust or anything else that will interfere with bed adhesion. And I think we're ready to start the print. Okay, well that's the print. Let me see if I can get it off. Got safety glasses here. You'll see why in a moment. I have a knife. This is just a snap knife, but I have sharpened the end of it. And I did that for another project at one point, but it's great as long as you don't dig in for getting under the edges of things like this. So let me see if I can work under the edge. And I can hear it cracking. I don't want to actually snap the knife off. I just want to use it to free it from the bed. It is pretty tight. Looks like I actually lost a little chunk of the blade there. Let's try with a spatula here. see the blade piece, but there is the part. I can see the marks left by the knife, but it's off in one piece. You can see the places where I scratched the bed by doing that, but the actual adhesion maybe pulled a little bit of the surface. I think I'm going to need to reduce the bed adhesion even more for something big like this. But it doesn't look to be warped, so let's take it out in the shop and see if it fits. And here's the finished part. I like the surface texture of it. Along the sides of the print, it's got this kind of matte texture. I know it's black. I know that's really hard to see on camera, but it's got this kind of black surface texture that makes the layer lines really hard to see. They're definitely still there, but it makes it hard to see. The part is very, very light. It's probably about the density of ABS, maybe a little bit less. And just trying to twist it, it does bend. I can bend it, but it's relatively stiff. I actually expected it to be a little bit more rigid than this. I think we'll just have to get it into the final application and see if that is going to work. Now, another thing that I noticed on this is that this register I designed and the slots and the size of the holes, they all came out a little bit small. The outside dimensions are pretty much exactly dead on, but the inside dimensions of the openings are a little bit small. And you know, I had read that this might be an issue. The filament is just spreading on the inside, or it's stretching around the inside. It's also possible we've got an overall shrinkage. I played around with the measurements for a while, trying to figure out, okay, could I scale it up a little bit and then shrink the wall, which would affect the outside and the inside, and get to the right dimensions? But judging by measuring the center to center distance between the holes, I don't think it's a shrinkage issue. I think it's an issue with the edges. For now, I just need a workable part. I will play with this later. So I went ahead and adjusted and printed another one. And this one came out, you know, the sizes are pretty much right on now that I've actually made the adjustments. And so I actually designed it oversized by just doing a push-pull on the surfaces to expand them a little bit, and got it to the size that I want. But again, it doesn't exactly match the model. So I've still got some work to do to figure out the scaling or the adjustment factors, or how to get this stuff to print. Feel free, I'm sure you're already doing it, go ahead and put down in the comments about how your printer doesn't have that problem. It prints everything perfectly, and if I would just get a decent printer like yours, then I wouldn't have that problem. And maybe someday I will. Maybe someday I'll be fortunate enough to have a printer like yours. The other thing that I did on this, because this adhered to the bed so strongly, is I lowered the bed temperature on this. And I lowered it all the way down to 30 degrees Celsius. And I don't know if you can see it from the reflection, but at the corners there was a little bit of lifting. In terms of the usability of the part, it's not going to matter at all. But at the very corners, you can see it's rounded a little bit from the reflections there of the lights. So I think I'll be playing around with it. I've tried some other prints in this material with a little bit higher bed temperature, and I think they worked a little bit better. In fact, you'll remember this part that I printed on the resin printer. This is the encoder mount for the electronic lead screw. And I went ahead and printed one of these in NylonX, and this is a thing of beauty. I mean, just look at that matte surface on the outside, and this thing is strong. It is rigid. It's more rigid even than the resin printed part. And so I am very happy with this, and I will definitely be using the material. Now, there's a little bit of flex in these big plates, but because of the cylindrical surfaces here and the geometry, this ended up being extremely rigid and very, very light. So I'm definitely going to play around with it for parts like this for sure, even if this ends up being a little bit too flexible. Let's talk a moment about cost. They really like this stuff and they're really proud of it. This is a 500 gram roll and it cost me $58. So we're talking about $120 a kilo for this filament. And so with that pricing and the amount of filament in one of these parts is about $2.50. Same thing with this, it's about $2.50. Now, I did some back of the napkin math, and a piece of aluminum flat bar at retail cut prices for a piece to mill this out of, that's about the same price, $2 or $3. So in terms of the actual cost of material, if we're talking about using it to replace a CNC milled aluminum part, the material cost probably about the same, and there's way less labor in this because I can just throw this on the printer and I can go do something else while it prints. But like I said, I am just really, really happy with this. This did require support material, so I just printed the supports up underneath, and I left the top of the supports fairly sparse, didn't do the dense infill, and so the underside of this surface that was supported is really rough. But for this part, it just doesn't matter. So I can design appropriately, use support material, and make complex geometries like this out of carbon fiber that should work very well. Let's grab some screws and a motor, and let's go ahead, oh, that's the wrong one. Let's go ahead and mount this up, throw it in the vise, and just see what the flexibility is like with real weight on it. Okay, the first thing I need to do with this is I want to tap these holes. I modeled them with threads in them, but they're 1032 threads, so there's just no way they're going to be sufficient the way they are. So I'm just going to go ahead and run a tap through it. Now, I don't want to cut the material. I'd actually rather just compress it into shape. So I'm actually using a form tap here. And I know doing this in a drill is not the ideal way to do it, but you know what? It's a really fast way to do it. So that's what I'm going to do. And I'm using the bubble level on the back of my drill to make sure that I have this oriented north-south. Now that is hot, and that's probably due to the carbon fiber in here. And I can see I've raised just a little burr around the outside there. Oh yeah, that comes off nice and easy, because after all, it is still plastic material. I'm trying to think about which way this is going to go on the lathe. This way. I'll drop that in. Register's a good fit. I'm feeling basically no movement. And I only put in some 1032 screws. Okay, I had to reset there for a minute to figure out what was going on because the register wasn't sitting in. I was actually compressing it in the vise. So there we go. That feels better. Now let's put in some 1032 screws. And the screws don't feel like they're bottoming particularly well. So this material is probably a little too soft to hold threads, at least threads at this size. So I'm probably going to want to run all the way through this and put a nut on the outside for this application, or maybe 3D print. You know, these are really short. Let me get some longer ones. Well, these screws are too long, but they'll be better than too short. We're just testing today anyway. Oh, that feels much better. Yeah. Screws were just too short. These were ones that were sized originally for going into an 1/8 inch aluminum plate. Now this will go into the back of the lathe and be held by screws in these slots. We'll simulate that by flipping it over, clamping it at about the same depth here in the vise. See how much flex we've got. Okay, we've got a little bit of flex in that direction, but that's not going to matter much because it's just going to hang like that. And so it's just going to be at whatever angle that is. The real interesting thing is the sideways force on the pulley. Because what we'll ultimately be doing is have a timing pulley on here. We'll use one with the right size hole though. Yeah, one like that. And then we'll have a belt on it. and that belt will be putting sideways force. So let me just sort of simulate that. That is going to be just fine. There's a tiny little bit of twist there that I can see, but it is not going to be enough. And you know what? If it does, once we get it on the lathe, it's easy enough to make one of these out of aluminum, but I think that's going to work. Well, that is pretty cool. We're going to have to find some other uses for this material around the shop, and I'm sure you'll see that in future videos. I am going to go put this on the lathe. I will do a video about that. I'm not going to do it today. I actually have to pull the backing plate off of the headstock and mill out some clearance to make room for the motor before I can mount this on there. And honestly, that's one of the reasons I've waited so long to do this, because I was waiting to have a full-size mill. In fact, I've got an e-mill in the shop now. That will make it a lot easier to do that milling. That's all I've got for you today. If you enjoyed this video, please give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. If you messed around with PA-CF or any other exotic materials with 3D printing, leave me a comment below and let me know how it worked. I always learn things by listening to you guys. Thank you for watching.